For our final project, we implemented a model and application to convert 3D volumetric meshes into dynamic physical audio models with real-time control over excitation forces and interactive control over model parameters. Physical audio modeling is a synthesis technique that directly models the structure of physical systems. This approach can produce audio with a natural and realistic character and leads to easily interpretable models with physically intuitive control parameters. However, physical audio models are also computationally expensive compared to other forms of audio synthesis. The technique of modal synthesis employs a source filter model to decompose physical audio systems into an excitation signal that drives a filter bank approximating the resonant modes in the physical system. This allows for physically realistic models that can efficiently produce audio in real time, and it's the technique we use for our project. Our application handles many kinds of 3D triangular meshes. For example, I'll load up this mesh of a teapot. I first need to convert the triangular mesh into a tetrahedral mesh. Next, I'll set the number of excitation positions to compute, which we can see distributed across the mesh vertices. Next, I'll select steel as the material property, and I'll generate the DSP code for the 3D audio model. To generate the audio DSP code, we do a finite element analysis to compute the mass and stiffness matrices, and then we find the resonant modes by estimating the eigenvalues of the system. To simulate striking the object, we model a hammer as a short pulse of filtered white noise, which we use to excite the filter bank. I can click on the excitation vertices of the mesh to simulate striking the teapot at different locations. I can also update parameters controlling the audio synthesis, such as the fundamental frequency, the overall decay time, or the ratio of decay times across the frequency profile. Our application also supports generating a 3D model from a 2D model. I'll demonstrate this with a profile based on the cross-section of an English bell. The profile is extruded around the y-axis. We can manipulate the profile shape, and we can control parameters like the profile tessellation and the number of radial slices to change the granularity of the 3D shape. Now I'll create a 3D model the same way as before by generating a tetrahedral mesh and generating the audio DSP code. Here's another model based on a 2D cross-section of a wine glass. Since calculating a 3D model can be computationally expensive, for our project we also investigated estimating a 3D audio model by carrying out an axisymmetric finite element analysis directly on a 2D profile. This avoids a ton of compute time by skipping tetrahedral mesh generation entirely, as well as making the finite element analysis and eigenvalue estimation much faster. Here's the same wine glass using our axisymmetric model. And here's the axisymmetric model of the English bell.